Now finally we can talk about the cohomology ring of the torus. Previously we put on R2 the coordinates x and y, and then we define alpha and beta to be the one forms on the torus, such that the pullback of alpha is going to be the form dx and pullback of beta is the form dy on R2. We have proven in the previous video that there do exist such alpha and beta, because dx and dy are invariant under translation by lattice element. Now our claim is that if we view the cohomology ring of the torus as a vector space, then a basis for that, an R basis for that, is just given by 1, alpha, beta, and alpha wedge beta. More precisely, 1 is gonna generate H0, right? And we'll have alpha, and beta is gonna generate H1, and finally H2 is gonna be generated by alpha wedge beta. Now the ring structure of this cohomology ring is already implicit from this description, because the multiplication just corresponds to the wedge product, right? If we want to be more explicit, we can say this cohomology ring is isomorphic to the exterior algebra on two generators of degree 1. These correspond to alpha and beta. This ring is generated over the real numbers by alpha and beta, right? And it has the following, subject to the following relation, which is just really property of the wedge product, which is that a square should be 0, b square is 0, and ab is equal to minus ba. Thus, this gives a description of the ring structure of the cohomology ring of the torus if we can prove that these 1 alpha beta and alpha wedge beta indeed form an R basis for the cohomology ring. Well, in degree 0, because the torus is connected, it's going to be generated by the constant function 1. So this is done. Now we want to show that H2, so in degree 2, this H2 of the torus is going to be generated as a real vector space by alpha wedge beta. Now previously we already know that H2 is isomorphic to R, so this really boils down to showing that alpha wedge beta is not the zero class in this cohomology, because any non-zero element of this vector space will span the whole vector space. Well, to show that the class of alpha wedge beta is not zero, it suffices to show that this integral, the integral of alpha wedge beta over m, is non-zero. But we can view m as being parametrized by the unit square, this square, the product of the interval 0, 1 times with 0, 1. Thus, this integral is going to be equal to the integral over that unit square of dx wedge dy, which is just equal to 1. And so we see that because this integral is non-zero, we see that the class of alpha wedge beta is not zero, and thus alpha wedge beta must generate the second cohomology of the torus. Up next, we're going to show that alpha and beta together generate the cohomology in degree 1 of the torus.